All right. According to the clock, the torturing starts now. I was looking over some of the material that we're supposed to be talking about today, and a couple of the things that I actually like about the textbook we're using. So every once in a while, they'll give you something that's kind of shaded in like we've got here, and that looks absolutely horrible, doesn't it? See if we can clear that up a little bit. Um, well, anyway. They're going to be little gray boxes of stuff that we can look at. Some of the definitions and terms in there are actually fairly important to know and understand. One of the big things that we're going to be dealing with in here is trying to remember what is the difference between, say, X bar and S versus mu and sigma. The stuff that I have on top here refers to a sample. The stuff that we have down here refers to a population. So when it comes to determining do you have a sample or a population, one of the things you have to do is look at or think about what question is actually being asked. For example, if I said, I want to know the average age of a student in my class, the population is going to be all of you that are actually in this class. So if I ask each one of you individually how old you are, you give me those numbers, I would actually be able to go back and calculate mu and sigma. However, if I'm just going to collect a sample of the population, because a lot of times the population that you're looking for is really large and you're never going to be able to talk to everyone. Uh, so if I randomly chose, say, 10 of you to try to figure all this stuff out, the values that I get for the mean and the standard deviation would be this X bar and S. Uh, so again, if we're trying to determine do you have a population or a sample, for the most part, the answer is you never have a population because you can generally never talk to everyone. Think about it if in terms of say you're trying to talk with people in Dearborn about who they're going to vote for mayor next time uh, there's an election. Can you really talk to every single registered voter in the city of Dearborn? You could. It would take a lot of time. And let's be honest, if some stranger walks up to your house, knocks on the door, hey, can I talk to you about politics? How many of you are actually going to open that door? And how many of you are going to be like thinking, I'm not going to say anything. I'm just going to ignore them. Maybe they'll go away eventually. So because of issues like that, you basically never have the population. You're always going to have a sample. And a couple things to keep in mind when we're trying to collect data. Uh, Even if you can talk with, say, the entire population, is there any guarantee they're going to tell you the truth? Probably not. So if we're going to do, just following along with what's in the textbook, looking at simple random sample, how would I go about doing that? I can put, say, everyone's name into a hat or something like that. And if I want 10 students, or to get the age of 10 students, I can just grab 10 names out of a hat. To be a simple random sample, every single one of you has to have an equal opportunity to be chosen. So if everybody's name goes in once, then that's going to be part of a simple random sample. On the other hand, if we're doing something where we're, say, having a raffle, uh, can someone buy more than one ticket? Yeah. So if we did a simple random sample of, say, people that bought into this raffle that we're doing, because someone might buy 10 tickets because they really want to win whatever it is, or they really want to support the cause for the raffle, versus some of you that'd be like, all right, I'll buy one, just you'll shut up and go away. Here's my money, now leave. Uh, we'd have unequal probability of everyone being selected. So when we're doing these samplings, we need to keep that type of idea in mind. Some things that can happen with a simple random sample. Uh, I may, like, let's say all of you live in Dearborn and all of you are registered voters in Dearborn. I know that's not true, but let's say that you are. I could say randomly sample a bunch of you, and if we assume that, say, the population of Dearborn is, say, 50-50 male and female, I don't really know what it is, but I might, out of the 10 people that get selected, I might actually have 7 or 8 women in that group. Does do those 7 women that would be in that group, do they adequately represent the population of, say, the entire city of Dearborn? Maybe, maybe not. Do the 3 men that I would select uh, represent the entire population of men in Dearborn? Almost certainly not. Uh, so for those of you that are trying to be marketing majors, or thinking about doing marketing, these are some things that you need to be careful of. You may have a really large sample, but if you choose too many people from a certain group, uh, there are ways to go around what you've got. But some of the ideas that we have when we're doing sampling, and this is if we're talking about marketing, or where's my mechanical engineer? See, so way, way in the back. So even if you're working at a factory and you're supposed to be pulling parts off the line to do quality control inspection, these are some of the things that you need to keep in mind. And with pretty much every method we do in here, there will be an assumption that these things are actually true. Then, of course, I have to put a little asterisk after that and say, unless otherwise stated. Okay. Samples are collected essentially independently. Two, they represent the population adequately. Three is essentially that the mu and the sigma doesn't change. And for some of the stuff that we do in here, we'll assume uh, there's some sort of a normal distribution, or something that is approximately a normal distribution for the data that we're looking at. Even if the data we're looking at uh, kind of looks like it's normally distributed, that's usually good enough for us. In practice, essentially nothing is actually normally distributed. It's just close enough for what we want to do, so we could go on with it, okay? So when we talk about collecting sample independently, what does that mean? And I have no idea if I spelled that right. I don't have spell check when I'm writing things out. But it has to be collected without, say, any type of what in stats we'd call bias. Um, so if we're doing a survey, so for those of you that are into marketing and you want to do a survey, or you want to convene uh, say a marketing group to see how effective your ads are that you're producing, okay? Asking each of the people that participates in your marketing uh, plan, they, if you start asking them in person and to say out loud, how did you feel about things? You can collect a lot of data that way, but the data is not collected independently. Why? There's something called peer pressure. Uh, if you're looking at doing some sort of a tasting, which one of these three items tasted the best to you, and you're thinking to yourself, eh, they're all pretty much okay. I'm not too excited about any of them. But the people that are next to you are like, oh my God, sample A was the greatest thing I've ever had. When they ask you, how do you feel about sample A? Did you just go from eh to it was pretty good? More than likely. Uh, if we do a marketing campaign and say we're asking you and a bunch of your friends as you're walking down the street and say either Westbourne or downtown Dearborn, how do you feel about whatever? And you've got the idea of, I honestly couldn't care less about this issue, and your friends are passionate about it. Are you going to look at your friends and be like, what? It's stupid. It doesn't apply to us. Get over yourselves. Or you can be like, yeah, just like they said. So again, you can collect a lot of data, but if it's not collected independently, uh, basically you can take whatever results you get, crumple them up and just throw them away because it's just not going to work out too well for you. You also have to make sure that the data you collect is representative of the population. So again, if Dearborn is, say, 50-50 male, female, and let's say the population is also, I don't know what the numbers really are, but let's say uh, 7 or 60% white, 30% Muslim or Arabic, and then 10% Hispanic and other. When you start talking with people, you got to make sure that you've got essentially enough people in each one of those groups. Which means sometimes the survey budget that you have to deal with can get very large. Uh, we'll do some calculations, I think, on Thursday, and we'll actually look at that sort of thing. Depending on the accuracy of the data that you want, your sample size can get incredibly huge, which means that more than likely, it's gonna, any data you collect is gonna come close to representing the population. And just for example, if you if your sample size is too small, you're most likely going to miss out on various groups because there is no group out there that is essentially what's called a monolith, meaning everyone in that group feels exactly the same way. Uh, so we have to watch out for that sort of stuff. The mean, so the population mean and the population standard deviation doesn't change. In statistical theory, this is always true, but in practice, things change. So again, if I ask everyone's age right now, and then ask everyone's age at say the end of the semester, there will be some of you that had a birthday during this semester. So you're now 1 year older. There's some of you that are here and enrolled right now that might not be at the end of the semester, which means the population mean and the population standard deviation will most definitely change. Uh, that can be a huge issue with a lot of the methods that we're dealing with because pretty much everything we're going to be talking about and dealing with in this class is assuming there is this actual population mean and population standard deviation. And the best we will ever be able to do is have hopefully a pretty good estimate of it. There's no guarantee that that's actually going to be true. And then the last thing here, we assume that everything comes from a normal distribution. Uh, if you if you look up some tutorials online, especially if anyone's interested in data science or business analytics, uh, the way that they discuss normal distribution is often somewhere between complete garbage and totally useless and wrong. Just saying. Uh, which means if you follow what they're doing, can you produce a statistical model? Yeah. Is that model going to be any good for anything if you violated all the ideas? Absolutely not. So again, you did all this work, take your work, put it on paper, crumple it up, and throw it away because you need to start over again. It's unfortunate, but these are some things that happen quite often. Uh, again, just looking at the book, there's simple random samples, and then there's what's called stratified random samples. For those of you that are into marketing, you'd probably want to use stratified random samples instead of just randomly picking people. So if we think about two groups of people that we want to deal with, if we have simple random sample, a lot of times you'll see it written out as SRS for simple random sample. You just pick people, blah, blah, blah. Let's say there are 100 dots there. And just looking at the way that I selected everything, uh, do these dots look like they're distributed throughout the entire space that I have here? Well, got nothing in here, got nothing in here, got nothing in this area either, which means anyone that, say, lives in those areas, they are totally excluded from being part of your marketing campaign. And if that's the target audience that you're going for, you just missed out. So you might come up with something that, say, the people in this group down here really, really love, but the larger group that's here and say the larger group that's up here is going to look at that same marketing campaign and be totally offended by it. So just some things that you need to think about. With the stratified sample, we can actually break this down into like little quadrants if we wanted to, or different areas. And now just here I've got 1, 2, 3, 4, 5 by 1, 2, 3, 4. So I've got 20 uh, different blocks here. Again, if I want to have 100 samples, I'm going to randomly pick 5 uh, people from each one of these groups or each one of these areas or whatever. Because the people are chosen randomly, that's kind of the important thing here by stratifying it and making sure that you get people that are in each area or each group. That's very, very important. Uh, so it is something that we need to be concerned about. If you, uh, I teach here, I also teach up at a U of M Flint. Up at U of M Flint, during the whole water crisis, which I'm sure most of you remember or at least heard about, couple of the issues that actually came up were when they went to do their sampling, they didn't bother to use simple random sampling. They didn't bother to use this stratified sampling plan either. They were supposed to collect samples from 100 homes. They collected them from, I believe, 81. And then some genius somewhere decided we're going to get rid of 2 of these data points because I don't believe they're real. And so it brought the sample population from like 81 or 80 or whatever it is to like say 78 or 79. And the end result was when they went out to these homes, And again, if you're going to be working with, say, some politician that you believe in, and you're going to be doing, say, uh, walking home to home to talk with homeowners about what issues are important to you, how do you feel about this candidate or whatever. Uh, they went to places where the homeowners would actually let them in, which is kind of important because they need to collect water from, say, the kitchen sink. If they can't grab it from the kitchen sink, grab it from, say, a bathroom sink or something like that. So you need permission to actually enter the home. So the people that you're going to be talking with have to actually be home in the first place. They have to let you in, secondly. And uh, then third, the samples actually have to be collected correctly. And if you've ever done sampling like that before, it is actually really, really easy to do. So how you screw it up, I have no idea. Um, but if you need to have make sure that you have this, or you're supposed to make sure that you have a sample that actually represents the population. And a lot of things that they did not work out that way. And the end result was the people that lived in certain areas of Flint actually had some major issues where the water in their part of the city highly contaminated with lead, and those areas were undersampled. So when you look at the actual results, uh, if you just use the methods that are taught in, like I used to be a biochemistry and physics major as an undergrad, some of the classes that we had, or if you've taken, like, say, an all-in-one engineering stats class or something like that, use the methods that you're taught in there because you don't know any better. You come to certain conclusions and then you look at certain data points and think, huh, this one's 104. Uh, Poisoning starts at about 16, and the next closest one to 104 is in the 40s. Maybe that 104 is wrong. Uh, but with the Flint data, when you actually look at it, it wasn't even close to normal distribution. But they were using the ideas that were taught in a class like this, which assumes a normal distribution, which again, you use the wrong assumptions, you do the wrong things, you get the wrong answers, and you should be taking your results, crumpling them up, and just throwing them away because you completely screwed it up. But the scientists and engineers that did the sampling up there didn't know any better, so they believed they were excellent because, hey, they've been doing it for 20 years. They've been doing it wrong for 20 years, but still they've been doing it for 20 years. And we had a prolonged poisoning of the folks in Flint. If sampling had been done correctly or the data had been analyzed even close to correctly, people in Flint still would have been poisoned, just not for anywhere near as long as they were. A couple other things that we need to look at. And again, the definitions of all these things, if you look in the textbook, are in the gray area, since I can't read any of that either. Uh, I'll just say it's talking about different types of bias. And it just says here, bias refers to the tendency of a sample statistic to systematically overestimate or underestimate a population parameter. It is often caused by samples that are not representative of the population. Uh, so what does that mean? So if we're talking about a manufacturing facility, and let's say you're filling bags of M&Ms or something like that. On the outside of the bag, it says that there's supposed to be however many ounces of candy in each one of those bags. If you were to ever weigh uh, how much candy is actually in those bags, it's never going to be exactly the amount that's on there. Part of the reason for that is even if one M&M just kind of slips while it's supposed to be going into the bag, just falls out or gets placed somewhere else, say on the shop room floor, uh, the bag is going to be lighter than it should be. But another source is if we're actually looking at whatever device it is that is weighing these things. Essentially, nothing you use will ever be 100% accurate. I've actually had some chemical analysis instruments. So these things are $50,000 to $250,000 a piece. And if you go in and you do an actual sampling and you look at the bias that these instruments create, can think of it as, say, you go home and you weigh yourself on your scale, and no matter what you weigh right now, the scale says you weigh 100 pounds. You look at that and you think, huh, I've either lost a whole lot of weight or I've gained a whole lot of weight, or uh, in my case, I look and go, not even close. Try again. So you get off, you get back on the scale. This time it says you weigh 103 pounds. You get off, you get back on again. It says you weigh 106, then say 108, and 111, 114, 116, 118, 121. And you just keep doing that. And no matter what you actually weigh, the weight on the scale continues to go up. That's actually another form of bias. And on several of the instruments I've had, that's essentially what was going on. At the beginning, when we're looking at toxins in soils and water samples, 70% of the total concentration is going to be reported. At the end of the sample run, everything's at 120, 130%. How do you look at this and try to determine what is, say, the actual concentration in these things? For our purposes, all we really cared about was, is it over some sort of a threshold value? So if we're talking about lead in water, is it over, say, 15 ppb? If it is, then we're interested in maybe relooking at that sample, trying to it again later. See if we get similar results. If we do, then we can go back and maybe report to that homeowner, hey, we found this issue with lead in your home. Here are some things you can do in the meantime, type of thing. And because the instruments we had kept adding a little bit onto the end of it, that induces a bias at the low end, a bias at the high end. It also means that the idea of the samples are normally distributed is no longer true. And because I could actually create a statistical model to predict what the bias was going to be on the next sample, those samples are not independent of each other. So huge issues. But one of the nice things was, if, say, 15 ppb is the cutoff and your instrument tells you there's one, you're not close. So even if that's 60% of the response or 60% of the total value, you're under the limit. So you're technically fine. A couple other types of a bias that they're talking about in here are selection bias and non-response bias. So selection bias, says here, refers to a systematic underrepresentation, or it could be overrepresentation of certain groups from in consideration of a sample. So again, if I'm looking at how do people in Dearborn feel about whatever, and again, it's, say, 50-50 male and female, but I've got 70% of my respondents are female, that would be a selection bias. There's also an issue of non-response bias. The textbook just says non-response bias refers to a systematic difference in preferences between respondents and non-respondents in a survey poll. So what does that mean? If you come to my house and you knock on my door, hey, we want to talk about politics with you, I'm not going to answer. But if you went to, say, my grandma's house and knocked on the door, because of when she was born, someone knocks or someone calls you, you better pick up, you better answer the door. You don't want to be seen as rude, which means If you do this door-to-door stuff, you can get a lot of, say, older people. Do 70 and 80-year-old people really represent your thoughts, hopes, dreams, and political ideas of everyone that's in here? Probably not. So that's another version of the non-response bias. Younger people tend not to pick up their phones at the same rate as older people. So you you get a lot of older people and their opinions on certain things. And then if you have enough people, again, you can try to come back and do what's called the weighting of the data. So if you've got a group of people that actually represents, say, 20% of the population, but in your sample it's only 5, multiply all the responses by 4 to bring them up to the 20%, essentially. You have another group that, say, represents 30% of the population, but it's 60% of your data. You cut all their responses in half, essentially. Okay. So 7.2, again, I can't read anything that's on there either. But we have some more definitions. Parameter versus statistic. It says a parameter is a constant, although its value may be unknown. A statistic is a random variable whose value depends upon the chosen random sample. So what is that kind of getting into? We can think of these as parameters. And then X bar and S. We can think of those as the statistics of interest that we are dealing with. Another couple definitions on here. Estimator versus estimate. When a statistic is used to estimate a parameter, it is referred to as an estimator. A particular value of the estimator is called an estimate. Nice circular logic there, right? So these would be considered our estimators of these guys. These would also be our best guess or our estimate of what the true value for these samples happens to be. One of the things that we have to keep in mind, so with these statistics, they are estimates of, or I should say for, the population. How can we tell how good our answers are actually going to be, how good our estimates are? Well, in that case, we have to create a confidence interval. Our stats software will, when we put numbers into it, will actually calculate these for us. So we do have the formula. This SE, for dealing with just one population or one sample or one group, this thing here is essentially going to be the standard deviation divided by the square root of n. If we are looking at the difference between group A and group B, the standard error is going to take on a completely different function than that. Again, you're not really going to need to know how to do that with the formula. How to do it with, say, a calculator, how to do it with, say, software, most definitely. And what we create here, is our confidence interval, which gives us a range of values where we expect to find the quote unquote true value for whatever parameter it is we're looking for. Since most of us never work with populations, we never know what that population average or population standard deviation is going to be. So the best we can do is come up with a range. And we can way to think about the confidence interval, especially if you're going to be doing anything important for decision making or planning anything. We don't know what the true answer is, but we're pretty confident that it's in whatever range we have. So just as an example, if we take a pop or a sample, and let's say I'm looking at what is the age of students in here, and plug everything together, and we get the confidence interval of 17 to 25 years of age. Is everyone in here going to be within that range of values? Maybe, maybe not. But is the range for the average age of a student in this class going to be in that or within those two values? Almost certainly. Okay. And that it, again, if we did a good job with sampling the data, if we randomly selected people or used the uh, if we grab different samples from different groups like we had for the stratificate or stratified random sample, we should get that should be a really good estimate for, say, the age of students or the average age of a student in this class. Does that mean we know exactly how old anyone is? If I was to guess anyone's age just based on this random sample, I would actually come back and guess that everyone was whatever the sample average was. Is my sample average going to be correct for everyone in here? Probably not. But is it the age that is going to be most likely correct for the most of you? Yes. So with while talking about all of this stuff as well, I'm not sure what you all learned back in your 301 class, but if we're talking about an average, or we can talk about a mean, uh, you've got many different ways that you can actually calculate this. The one that most of you are probably most familiar with is going to be something like that. But we can also use another term here, expected outcome. Of the three, uh, expected outcome has the most broad use because anytime I'm talking about an average, so if I'm looking at what's going to be the average on the first exam in this class, that's going to be an expected outcome. If I'm doing some sort of a regression model like we're going to be doing later on in the class, uh, asking what is the average of all of these things doesn't make sense, but what is my expected outcome assuming something? That actually does work out. So let's looking at some of the example problems in here. And for whatever reason, they're assuming that the population is actually known, which it basically never is. Um, Sampling from a normal distribution, uh, central limit theorem for the sample mean. Uh, One of the things that you're going to find when you look at a lot of statistical textbooks is they will tell you, just as an example, and our textbook is telling us this as well. If we're trying to figure out, say, what the average is, we're either going to be looking for mu or x bar. But what they tell you is use x bar if you have somewhere between 1, in our textbook says 1 in 29 samples. Uh, if you have 30 or more, you should use mu and assume that you've got the population. Other textbooks will tell you that the cutoff there is going to be 50. Others will say it's 60. Others will say it's 100. Uh, I tend to ignore all of those because a lot of these are based on assumptions that are not true anymore. If this was, say, the 1970s, yes, we are going to do this. Yes, we are going to talk about it this way. Is it currently the 1970s? What do we have now that you didn't have in the 70s or the 40s or the 20s in 1920s, not 2020s? What didn't you have in 1880 that we now have now? Computers, right? Which means uh, using the cutoff value that they're talking about there is unneeded and unnecessary. It's still something that comes up quite often. And if, again, if we didn't have computers, if we didn't have calculators, uh, using these assumptions makes the math behind all this stuff so much easier to deal with. Because part of the reason is if we're trying to come up with a confidence interval for either one of these, uh, even if we have over 30 samples, we're still going to have X bar plus and minus a z-score times a standard error. The z-score is a function of what percentage of the data do we want to be in our confidence interval. We could say we want a 90% confidence interval. We could say we want a 95, a 99, 99.9, whatever that happens to be. The only thing we have to do here is know what percentage we want. So we can then go to a table of values written in the textbook, figure out what the z is, and we're done with it. If we're dealing with the confidence interval down here, the t value here is a function of whatever percent you want and the sample size that you want, which means if we are going to try to look at that value up in a table, quite a lot of the time you can't even get the exact value because the tables that you use in the back of the book will say uh, discuss n or degrees of freedom. And then they'll have, say, a column that says 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 15, 20, 25, 30, 35, 40, 50, 100, 150, 200, 300, 400, and so on. So if you've got 28 samples, you can't even look up that number. But our software does it for us. And in everything that I plan on giving you, test you all on and homework and stuff like that, we're going to be assuming that you have a sample, not the actual population. Uh, this is my first time using this textbook and already finding I don't like the order they're doing things in, but we get to deal with it. The three types of peas. When we're dealing with uh, mu and x bar, these are going to be, or these can be used for essentially any type of data that we're looking for. These guys down here are for looking at proportions or percentages. And depending on uh, what textbook you use in or you use, you may have P or P sub 0. Again, that's going to refer back to the true value for that population of people that you're looking at. You may have P hat, which is this line above, or it could be P1, or it could be PA. These are all estimates. So thinking back, what's the difference between mu and x bar? X bar is the value we found by looking at a sample. Mu is supposed to be the known parameter. Same thing here. These are based on the population. All three of these, because of the different places you can get your information from, are three different ways of trying to describe the same thing. It's the proportion you get from looking at a, say, a sample of the population. And then this p hat down here is yet another estimate that we make. So if we go in and we calculate these, and let's say a bunch of us go in and calculate what the proportion is going to be, the p hat ends up being an estimate. It's going to be used quite a bit later in the semester, but our estimate under, say, certain conditions. So what are we talking about here? I'm hoping that everyone at least knows a bit about sports. Even if you don't like sports, do you at least know a little bit about sports? So if we're thinking about, say, basketball, and this is actually going to be a thing that we look at a little bit later, watching one of the ESPN stations many years ago, they're trying to figure out what the heck is wrong with LeBron James, because when they looked if you look at what is his performance, what proportion of free throws does he make throughout his career, it was essentially 81%. But over the last 4 games, it was like 76%. Oh my God, is LeBron James hurt? Uh, and when you actually do the math and you look at the data they're using, the answer is no. Why? We generally don't know what this value is, but when we look at the confidence interval, it went from an average of like say 75 or 76%, whatever it happened to be. On the low end, it's going to be say 68%. On the high end, going to be 84%. Does 0.81 fall within that confidence interval? Yes, which basically means if the two people that had been talking about this gave, say, any one of you at the end of the semester anyway, $20 to do the calculation, they could have saved ESPN 6 minutes of airtime. And considering how much they charge for commercials on ESPN, that's the $20 you just got paid saved ESPN maybe $1 million. But no, we can't make that investment. We need something to talk about. Ugh. So they did that sort of thing. Again, uh, when you're looking at data like this, especially if we're talking about proportions, it comes from basically the binomial distribution. The proportion we're looking at has to be a value that's between 0 and 1. So we're looking at uh, 0, say 0% to 100% if you want to think about it that way. What's a thing where you generally get values that are between 0% and 100%? Grades. How many, what did you get on the exam? Usually you talk about, hey, I got an 87% on the exam, right? As opposed to, uh, I scored 165 points. Because if someone tells you that, what's the next question that you're going to ask? Out of how many? 165 out of 200. Not bad. 165 out of 10,000. I don't know. Is that good? Is that bad? Um, so with all of these, there's going to be the same type of formula. With proportions, just because n is generally a large number, say hundreds to millions and all that, we can still create our confidence interval. And it looks almost exactly the same as our confidence interval that's up here. Uh, but what all the software does, it always uses the z value. Why does it always use the z value? Because that's been standard practice for pretty much for freaking ever. So if we're looking at a population with where n equals 20, does it make sense to use the z value? No. But even in a case like that, we're still going to use the z value. And part of the reason also is the more samples you get, the closer this t value looks like the z values. So at a certain point, uh, just as a point of reference, if I have, say, 90 samples or something like this, the t value for a 95% confidence interval is going to be, say, 1.9856. If I look at it for the z thing up here, it's going to be like 1.983 something. Do we really care about the third decimal point there? These are estimates anyways. Probably not. For those of you who have, say, OCD or were tortured back in, like, say, high school math or even college math, you need to put down as many decimals as there are. No, not here, because we're already creating an estimate. And the talk that I told you guys about last week actually got pushed back. I'll make an announcement about it. Uh, so it's not next Tuesday, it's the 16th. But we're actually going to find there is that even when we do a really good job of all these things, uh, sometimes it all takes a crap on you, and you end up with essentially nothing to deal or nothing that you can do. So with all of these, we're looking at essentially one sample and trying to get an idea about what that one sample is, so we can have some practice with it. We'll try creating some confidence intervals, and we're going to be using a Minitab to do this. And then we can also look at uh, our proportion estimates. To make it easy, I'm going to say the proportion is 50%. And then N is going to equal, let's say 50, 100, and 1000. So for this one, I get to actually share my screen. So try to make this a little bit bigger so any of you that are trying to copy down these numbers, you can still see what they are. If you have Minitab open, I don't need it to be as big and obnoxious as it is there. We can actually do these calculations, and I can go to stat, and I'll make another video of this where we go over a couple more example problems. So those of you that aren't logged into your computer right now, you can follow along with it. Well, you can go to stat, basic statistics, and then just because of what we have here, we're going to be looking at a one sample t-test for this guy side, and then the one proportion down here. So I'll just write this down. So using everything that I've got here, look at the one sample t-test. And there's some things in here. So it says one or more samples each in a column. So if I gave you a bunch of raw data, that would be the correct thing to use here. But I'm giving you what's called summarized data. So I have to click on here, and you can see that the other option here is summarized data, okay? So I can click on the summarized data. It's now asking me what is the sample size, what is the sample mean, what is the standard deviation. So for this first one, sample size, N is going to be 5. Sample mean is 3.5. And the standard deviation here is going to be 2. Something we'll get to, I think, in the next chapter is we can do this perform hypothesis test. Spoiler alert, you're going to have a couple problems like this on your first exam. And a way that we can think about this is, let's say we're looking at a new medication, and we know that the effectiveness score is 3.5. And let's say we want to compare that effectiveness score to the previous medication or the standard of care that's usually given, and let's say that standard of care is 2. So we could perform a hypothesis test and type in 2 down here in case that's what we want to look at. With Minitab, there are always options. So we can set the confidence level here to 95%. 95% is the standard confidence level, unless I or whatever research you're looking at states otherwise. When they say my confidence interval was, and those give you the numbers, they're using a 95% confidence interval. And one of the things that we can do here as well is we can look at is the mean different from the hypothesized mean or the standard of care. This gives us a two-sided test, or we can say, hey, we want to see if our mean is greater than the standard of care. That's a one-sided test. That'll be for another day. So I'm just going to click on OK here and click on OK here. And you can see when n equals 5, the confidence interval comes out to be 1.017 to 5.983. If I make n equals 10, so again, I can go back. The stuff we have down here, talk about that later. But I can go back, so I can go to stat, basic stat, one sample t. Now I'm going to change that from 5 to 10. Again, click on OK. Our new confidence interval here is 2.069 to 4.931. When n equals 100. So again, I can go back to stat, basic stats, one sample t, make that 100. Click down here on OK again. And our new confidence interval here, 3.103 to 3.897. So, and we're comparing that against 2.0. What did I say these confidence intervals were? They're our best guess as to what the true value is for whatever it is we're looking at. When we only have 5 samples here, the confidence interval goes basically 1 to 6. Is 2 a value between 1 and 6? Yeah. So we don't know what the true effectiveness score for this new medication is. Based on 5 people, we think it's 3.5. Our estimates say that it could be anywhere from 1 to 6. Since 1 to 6 includes 2.0, we'd basically say there is no difference between standard of care and, say, this new medication. If we double the number of people we have, all of a sudden we've got it to a little bit over 2 to a little bit under 5. Is 2.0 within that confidence interval? No, it's not. So 2 would be a value that we necessarily would not expect from this new medication for the average effectiveness score, which means that it looks like it's actually a better product. When we get it to this n equals 100 thing here, is 2 within that range? No. So a couple things that are happening here. As the number of samples we get goes up, our confidence interval actually shrinks. The upside of that is if we're looking for really, really small differences between groups, I'll just get more samples. The downside of that is um, we might know that uh, we could look at what's called a statistically significant difference, but versus a practical difference. Uh, so for example, if you're on a diet, is losing 2 pounds versus 3.5 pounds a practical difference? Maybe, maybe not. If you already weigh 80 pounds and you lose 2 versus 3.5 pounds, is that going to be a big thing? Yeah. If you weigh 270 pounds like I do, what's the difference between 2 pounds and 3.5 pounds? Did I get my meals supersized at McDonald's or Wendy's or whatever? Did I go for the triple baconator at Wendy's and get it biggie size? So probably depending on the situation, the way that we want to look at these things will change. For the proportions that we're dealing with here, so I'm going to make this small again. I can go to stat, basic stat, and then one proportion. So again, it says one or more samples in each column. We don't have any data in column. We have summarized data. So we click on there. So here, it's looking at the number of events versus the number of trials. The number of trials is n, so you'd at least know that that's going to be 50. The number of events, if you're using Minitab, apparently, last time I used Minitab to do this, I could actually put in the percentage that I wanted. Now I have to put in the number of events. So the number of events is equal to whatever p hat happens to be times n. So what's 50% of 50? In this case, it's going to be 25. Again, options here, one-sided test, two-sided test. What do we want to look at? So I'm going to click on OK. And we've got n equals 0.357. So 35.7% to 0.643. So we go out, we're trying to take a survey. What candidate are you going to vote for, or which of these two candidates are you going to vote for? And we come up with this estimate of 50%. And then the confidence interval, 35.7% to 64.3%. So plus or minus what, 24% roughly? If you're into polling, is plus or minus 24% good for anything? Absolutely not. So here, this was a n equals 50, I should say. If n equals 100, again, our confidence interval, go back to stat, basic stat, one proportion. So this time, the number of events is going to be 50% times 100. So 50. The number of trials is going to be 100. We can click on OK. Oops. Let's try it with 100. So the error that just popped up there, and if you do this with a graphing calculator, I'm trying to say there are 50 events out of 10. How can 50 things happen when you only have 10 opportunities for it to happen? not going to work out too well. So I click on there, and this comes out to be about 40% to 60%. If I do this one more time with n equals 1,000, so go back to stat, basic stats, one proportion. So 500 out of 1,000, click on OK. And the value here is about 47 to 53%. Okay. So again, the more people you have, the smaller the confidence interval is going to get. The smaller the confidence interval, the better you are at estimating whatever parameter it is you're interested in. With proportions, the confidence interval is based upon the starting number that you're dealing with. In this case, we started at 50%, which is essentially the worst value you can use here. So just in general, if you are a marketing or a student in marketing, and let's say you're trying to figure out how many people do we think are going to like the product that we're putting out, we want to use the worst possible number for this, which is going to be 50%. Then we can go back and back calculate how many people we need to talk to based upon that. What's going to happen is if we're looking at, say, the number of people that well, put the number of people we need there, and the proportion we're dealing with here, at really low values, it's going to be a certain thing. Then at high end, it's going to be something else. And it's actually going to look something like that. Where at 50%, you end up using the most amount of people. So even if you have a pretty good idea that, say, your product is better than what's already on the market, and you think that, say, 60 to 70% of people in the market are going to want to buy your product, you still go back, you still say, we're going to start at 50% and go from there. Okay. So I know that was a lot, and it was. But we're going to be doing these things over and over and over and over and over again. So if you didn't get it the first time, I think there's probably only going to be 10 more opportunities for all of these throughout the semester. So if you can't get it by then, I think it'd probably be too late to drop the class, but I wouldn't worry about it too much. So for right now, I'm just going to leave it at that. On Thursday, we'll have a little bit more time to talk about these things, and I'll actually have you do a couple problems using Minitab. All right. And those will be things that you actually have to turn in. So if there are any questions, feel free to ask. Sure. No, that's a problem. That's fine. In my Canvas link up in Flint, there's actually this thing right on there that says Zoom. And I can post everything to, or record everything through there, and all my students have instant access to it. I don't have that option on Canvas here, which means I'm going to have to start yet another YouTube channel, post things on YouTube, and then send you all the link. Which means when it comes to these videos, I am doing a cloud recording on them. So as soon as I hit the stop button, it's going to start processing it. The recordings usually take about an hour before I get a notification that they're ready. Once they're ready, I then have to get back on my laptop, download the video onto my computer, then depending on where I'm at, that can take some time, then download it from my computer, upload it to YouTube because yeah. So depending on the upload speed, that's going to be another thing. Uh, I've actually had this whole process take 3.5 hours before. And that's when I'm on top of everything. Dear God. But in general, Tuesday lecture should be ready by Wednesday. Thursday lecture should be ready by Friday. The first lecture we did, I don't know that we really need to post that since this is the new stuff. And I will be doing the web extras too. Same type of format. All right. No one's told me anything. From my experience, other colleges and universities, only full-time faculty get SIs. I don't know if that's true here. For the stats class I'm teaching at UM Flint, allegedly I have one. I have no idea what their name is. I have no idea who you talk to about talking to or to get the name of that person. And when I ask other people in the department, they're like, yeah, you got one. What's their name? Oh, I don't know. How do I find out? Oh, let me ask around. So, but there is tutoring. The business school does have tutors that are available for all of this stuff. Uh, I'm going to try to keep it as close to what's in the textbook as possible. So that when you go to the tutor, they can hopefully help you. Well, we're going to cover a couple of things that I don't think other classes are. So that'd be fun for you. Yeah.
I'm assuming we're gonna need like notebooks in this class because we'll be turning in like homework specifically, correct?
There's gonna be, like I said, next class period, gonna give you a couple problems to work on using Minitab, just to make sure that you know how to use Minitab. It's gonna be basically doing the same things that I just did here. And then I'm have you write those things down and then try to have you guys or have you interpret them to make sure that you've got all the thought processes that you have are correct for it. All right.
Yeah.
Yeah.
Okay. I was all prepared for my DS class that was originally scheduled for, and I switched it literally last week, the last second, so I was not prepared. Well, I should have been.
Yeah. No problem.